So will I give you your
iron
key?
traps,
Okay.
using molecules, different types.
Any questions? All right. So we were talking about weak interactions and in particular how these various masses come about. The Higgs mechanism. And there are the fields, first of all, these are the fields that the up and down, the W bosons act on simply. And that's UD, nu E, and we call this electron nu, the electron neutrino. The second family is charm, strange, nu, mu, and mu. And then the third family is top, bottom, nu, tor, and tor. And what I decided to do in my notation, this may not be the best notation, probably a subscript capital F for family or flavor would be better. Anyway, these are the flavor eigenstates, and the W's act simply on these. Act simply on these flavor fields or eigenfields. I think I'll just write fields. Okay. Now, remember we had these various Higgs terms. We said that in the vacuum we had something like minus Cu, Q bar left, sigma 2, H star, UR, plus complex conjugate or Hermitian conjugate. And this gave us 1 over root 2 V this was I, C sub U, U left dagger, U right minus I, C U star, U right dagger, U left, and then the vacuum like that. So this was a mass term for the up quarks, and this is actually the more complicated mass term. The up quarks have somewhat more complicated mass term. The mass term for the down quarks was simpler. It was something like this, 1 over root 2 V. V is 246 Jet or something like that. And then this was minus CD. Cu and CD are just parameters that we choose to fit the masses. And this was D left dagger, D right minus CD star, D right dagger, D left, like that. And this came from a simpler structure. The simpler structure was 0 minus CD, Q bar left, Higgs, D right plus Hermitian conjugate or complex conjugate. And so this is the simple case. We know that Q goes as SU2 left, H goes as SU2 left, so Q dagger H is invariant. Over here, last time I showed that sigma 2 H star, where H star is H1 dagger, H2 dagger, and that's actually the positive one, this is the neutral one, dagger, that this thing transforms as SU2 left, And so Q left dagger, it is invariant. So those are the invariances. And what we have, of course, is that this same Higgs term interacts with all these different up quarks, down quarks, and so forth. So in other words, what we have is the sum ij equals 1 to 3 minus c sub d, but now ij q bar prime li h d prime right j, and then plus, I'll just write plus hc to make things simple. So these are the terms that give rise to the down quark masses, and what we can have is you see a term, all of these terms are invariant, in other words, and so we have to consider that in general all of these would occur, rather than up to this point we were just saying, well, we're just going to have I equal j, and so we would have family 1 down, family 1 up down, and family 1 down, and then that would give us a mass for a down quark, and it would be the same mass as for the flavor down quark. But in fact, symmetry allows us to consider all of these, and they all apparently occur. And so, in other words, what this does look like is something like this. Once we have symmetry breaking, this thing gives us V over square root of 2, sum on ij equals 1 to 3, minus CD ij, d prime dagger li, d prime rj. Left and L and R stand for left and right, of course. And so that's something that we can rewrite as sum ij equals 1 to 3 minus d prime li m sub d ij d prime right j plus hc and so forth. And so we have a mass matrix then for the down quarks that's a 3 by 3 matrix, and the ij element is V over square root of 2 CD ij. So these are 9 complex numbers that are just sort of chosen so that in each case, chosen, actually we don't quite, when we're at this stage, when we were at this stage, when we were considering separately each family and not considering the mixing, then we would pull out of our nose what this value was, and we would say make it positive, and then we would get a mass, and everything would be fine. Over here, it's more subtle. It's that we have to deal in general with a 3 by 3 complex matrix. But like any 3 by 3 complex matrix, we can perform a singular value decomposition and write this as, well, now I see I'm writing it in 2 different notations. The standard notation for the singular value decomposition, for some reason, is this way with mixed Roman and Greek letters. U and V are unitary. Sigma has non-negative values on its main diagonal, or its main diagonal if it's square. If it's not square, you see the singular value decomposition applies to an arbitrary matrix, an arbitrary complex matrix, even if it's oblong. In other words, 3 by 9, or 9 by 2, or 14 by 27, whatever. You can always do a singular value decomposition. When you do so, when the thing isn't square, then the dimension of this and the dimension of that, these are two different dimensions. And this thing is oblong or rectangular rather than just square. In any event, these masses then, sigma then is, traditionally the biggest mass comes first. So this is the mass of the B quark, mass of the charm quark, mass of the Dan quark. And roughly speaking, this is, I don't know, 4 or 5 JeV, this is maybe 1.7 JeV, and this is a few MeV. Question? I see a puzzle.
I'm trying to figure out why you was strange charm down and not like down straight. Maybe bottom? No, I don't.
Oh, yes! God damn it. Yes, this is strange. Okay, so pointing out an actual error as opposed to asking a question to get a second candy.
Oh, thank you.
Yeah, of course it's.
Okay.
Yeah, that's what my notes have. It's.
The left arm got low.
I should really read my notes when I'm lecturing. And so what I'm going to do in the future is I'm going to write MD in this way as LD sigma D RD dagger. And why am I writing it that way? Well, because the L, this MD comes from really the H and the constants. And so the one on the left, there's an L on the left, and then there's an R on the right. So it looks like that. And so what we can say then is that the right-handed mass fields or mass eigenfields are this. They are R dagger D I J, flavor right-handed J, and so forth. And the D dagger left I, this is again mass eigenfield, is D flavor dagger L J L D J I, for example. And so if we adjoint that thing, we get that the left-handed mass eigenstate field is L dagger sub D I J D left J. Okay, so these are the left and right fields that are mass eigenstates, and they, of course, correspond to the same mass. We're talking Dirac masses, Dirac fields, and let me just emphasize that the nature of a Dirac field is that you have a linear combination of two fields, phi 1 plus I phi 2, and both have the same mass. So that's what a Dirac field of spin 1/2 is. But in general, a charged field is always of this form. Two fields of the same mass we combine in this complex way. All right, so let's see. All right, and for the up quarks, we have a similar situation. There's an up mass matrix. The ijth element is IV over square root of 2 Cu ij. And this comes from terms like this: sum ij equals 1 to 3 minus Cu ij Q bar Li sigma 2 H star U right J J minus HC, or plus HC actually. The sigma 2 tosses out an extra I, so that's why that turns out to be that. Okay? And we're going to set this thing equal to LU, sigma U, R dagger U, and sigma U, if I can get this right, I'll read from my notes. Mass of the top quark, mass of the charm quark, mass of the up quark. And this is around 176 or something GeV. Maybe, I don't know, 1.7 GeV and a few MeV. And since I got this one wrong, this one is, I don't know, maybe 160 MeV, something of that order. Okay. And we have the same relations relating the flavor quark to the quarks to the so in particular the right-handed flavor quarks are R dagger, mass, flavor, and the left-handed ones are use of L is L dagger D prime. So these relate the flavor to the mass for the two kinds, and once again the masses are the up and down quarks occur in combinations such that well, what happens of course here is with this structure, let's see, maybe I should illustrate that for the down case. What you've got here is, let me rewrite that term up there as Q bar prime left, and then it would be MD D prime right. And now I'm using a 3x3 three vector notation. This is a triplet of doublets, and this is a triplet, and this is a 3x3 matrix. And then we can rewrite this as Q bar prime left L D sigma D diagonal R dagger D D prime right. And yes, and so now we see that the mass eigenstates dr are R dagger D D prime right. I hope that's what I wrote. Yes, that's what I wrote. Okay, so that's the way it comes out, and then the left-handed flavor adjoint states times LD like this are the adjoint mass eigenstates like that, and so then we get that Q left is the adjoint of that, and so that's LD adjoint Q prime left. And that's what I wrote here then. So that's how the thing works. And what we have then is a 3x3 matrix. And or two 3x3 matrices. And if we look at the right-handed covariant derivative, then it's pretty simple. It's just d mu minus IE tan theta weak z mu cubed plus IE a mu cubed. So the right-handed covariant derivative acts the same way on the flavor as on the mass eigenstates. No difference. But the left-handed one is different. And in particular, the left mu, well, it's 2 by 2 identity, d mu, plus I e over root 2 sine theta w. And now it's w mu plus t plus w minus mu t minus plus I e over cos theta weak, or theta Weinberg, z mu t3 over sine theta w minus sine theta w q, and then plus I e mu q. Okay. Now you may think this is a little bit complicated because it's a long expression. However, and you may think that by contrast QCD is simple. Because QCD is just, I mean, it's, the covariant derivative is much simpler, but actual calculations are a nightmare because you have to consider so many terms, and of course there are infinitely many terms, so you have to, it's very difficult. And in fact, it's very technical. There's some new methods have been developed that simplify things somewhat, but it's still a nightmare compared to the weak interactions. The weak interactions are, you will learn to love the weak interactions if you specialize in particle theory. Okay, so those are the covariant derivatives, and now what do they act on? Well, they're acting on u bar prime right, well, d right, u right prime, and this is the same thing as u bar right, d right mu, u right. So for the right-handed fields and the right-handed covariant derivatives, you can start with the primes, which is the way you do start, and then you get to the mass eigenstates. By the way, let me mention, when we do physics, the first thing we do is we analyze the part of the theory that we know something about, namely the quadratic part, and we diagonalize that. So that means that we are always dealing from the beginning with the mass eigenstates, the eigenstates of the quadratic part of the Hamiltonian, which we can actually analyze, understand, diagonalize, and so forth. So everything is defined in terms of the mass eigenstates to begin with, and that's how things propagate, because it's the quadratic part that's the main part. Everything else are these interactions. And in the case of the weak interactions, the interactions really are weak. They're weak, of course, because they're at most of electromagnetic strength, and secondly, they're a very short range because the Higgs mechanism gives high masses to the W and Z and limits their range to very tiny fractions of a fermion. So the strong interactions, for reasons we don't really understand, have a range of about a fermi, but the weak interactions fade far shorter than that. And in fact, you can figure out what the distance is. 140 MeV gives you a Fermi. The W is like 90 JeV, and so that's a factor of 700,000, is that what it is? Anyway, huge. Huge. Big number, okay. So what we have then for the left-handed ones is we have something like this. U bar prime left d bar prime left, d left mu, u prime left, d prime left, and I'm thinking of this as a triplet. So this is all of the quark fields, let's say. And what we can do then is we can say that u prime left and d prime left are related in this way. U prime left is L dagger u prime left and so forth. No, u is that. So in particular, u prime left is L left. L left? No, it's L. U left. So the flavor eigenstates are u times the mass eigenstates, and here the right flavor eigenstates are this matrix R times u right. Okay. So when we rewrite this, what we get here is u bar left L dagger for the up quarks. And I guess I should have put in the up. Well, there are the up ones. So if this is all up, then this is RU, and over here, well, I have RD. Okay, all right. So I guess it's okay. So this is U bar left, L dagger up. So this is a 3x3 unitary matrix. D bar mass now, L dagger D, and now the covariant derivative, and then the flavor eigenstates are u's L sub u times the mass eigenstates and so forth, and so this is LU up left, LD down left. So that's what the whole covariant derivative looks like, left-hand covariant derivative looks like on the quark fields. And now if we substitute this expression, which is only about 12 feet long, in here, then what happens? It becomes almost the same thing, and the difference really is this, that in these terms, first of all, these things have no effect because this part of the covariant derivative is diagonal in up-down space. And so what happens is L dagger U hits LU and you get the identity. L dagger D hits LD and you get the identity. But in the T plus and T minus case, you get something different. And what happens is that effectively T plus goes into what we can call T plus, I'll just write it as C. C is for Kabibo, but it's really CKM. Kabibo, Kobayashi, and Maskawa. Okay. And what does this look like? Well, it's 0, L dagger U, LD, 0, 0. Instead of having a 1 here. And T CKM minus is 0, L dagger down, LU 0, 0. So it looks like that. So that's basically what happens. And the way this comes about, of course, is that the T plus acts on this doublet, and so you get, maybe I should write it out, T plus LU, UL, LD, DL, U bar L, L dagger U, D bar L, L dagger D. Okay. So this thing then is U bar L, L dagger U, D bar L, L dagger D, 0, 1, 0, 0, LU, UL, LD, DL. And now, if you multiply that out, you see what happens is you get U bar L, L dagger U, U bar D, L dagger D, and then this becomes LD, LD, DL, and then just 0. And so this then is U bar L, L dagger U, LD, DL, and then we can rewrite that as U bar left, D bar left, 0, L dagger U, LD, 0, 0, U left, D left. Okay. So that's why, that's T plus CKM. All right, so what happens then is that the W plus and the W minus move a massive up quark into a linear combination of massive down quarks and move a massive down quark into a linear combination of massive up quarks. And this one matrix here, this matrix here is, of course, the adjoint of the one that's up there. All right, you can do something else. And in fact, this is what's normally done in the, I should have mentioned this in my notes, I'll have to add it. What you can do at this point is you can say, well, I've got these, what should I say? Let me try to get this straight. I just had a thought, now I'm wondering if it's right or not. All right, if I'm not sure, let's forget about it. And if it comes to me again and turns out to be right, I'll tell you about it next time. Okay, so this is what we've got then as our covariant derivative. It is, we can just rewrite it as this covariant derivative, and we just replace this by CKM, and now we use this with the mass eigenstates. All right, so all right, now of course with this 3x3 matrix we have a certain amount of freedom because we can always multiply a field by an arbitrary phase and redefine the field. So we have 6 fields, 6 quark fields, so we have 6 phases that we can eliminate. And the insight, which was back in something like 1976, how it is that something this simple didn't dawn on anybody until then, I don't know. But actually, most of the best ideas in physics are actually very simple. The idea was that you have a 3x3 complex matrix, this LU dagger LD, and now you can remove 6 phases. Well, when you remove 6 phases, it turns out if you analyze it correctly, you find that you are left with 1 phase. And that 1 phase leads to violations of CP invariance. Of course, back in the 50s, Yang and Lee and the Dragon Lady, Madame Wu, at Columbia pointed out that, or showed that the weak interactions violated parity. And the funny thing about all that is that people thought that the weak interactions conserved parity, because they thought everything conserved parity. You had to have left-right symmetry. And then Yang and Lee said, well, we don't really know that. Maybe we should test it. And then when Wu tested it, she found that not only was it broken, it was maximally broken. And it's not just the little, it's the whole thing. Because, and the reason is that the W's only interact on the left-handed fields. They don't interact on the right-handed fields. So it's maximally broken, which is something that's very hard to understand in as much as the rest of it, the Z and the A, and the gluons of QCD, and the gravitons, all those things, as far as we know, which may not be very far, but as far as we know, are preserved parity. Well, with electrodynamics, we're pretty certain that they're preserved parity. But the others, we're not certain of. Well, people think that everything else conserves parity, and so we've got something that's hard to understand why part of the theory conserves parity and part of it doesn't. And that's kind of confusing. It's very confusing, I think. All right, anyway, so that so much for parity. But after people realized in the 50s that parity was not conserved, they noticed, well, first of all, there was a theorem that in any field theory, CPT, charge conjugation parity and time reversal, is conserved. And they thought, well, for practical purposes, maybe P is broken in the weak interactions, but surely CP is okay. And so for maybe another 10 years, CP was okay. And then Fitch and Cronin, in some experiments on kaons, neutral kaons, showed that CP was not. That was 1964. Fitch, let me see if I can spell Fitch. Fitch and Cronin. I think Cronin died recently, or Fitch did, one of the two. I think, maybe not. I hope they're still alive. Anyway, one of them, by the way, is very amusing. Gives marvelous talks in which many very clever jokes. So I think it's Cronin. Matthews would know because he's interacted with them. All right. So the deal is they show, and so one phase, and what Kobayashi and Moskawa showed was that if you use the 6 phases, if you use the freedom to define the 6 phases, you still have one phase left in the CKM matrix, and that could lead to CP invariance. And it's very possible that most of the CP invariance is due to that phase, but of course, so far I've just been talking about the masses of the quarks, and well, in a moment I'll get to the leptons, but the charged leptons are pretty much the same story. What you also have are the neutral leptons, and I'll get to them shortly, so I ought to get moving, I guess. Anyway, it's this one phase probably may lead to most or all of the CP non-invariance in hadronic processes. But I don't know. Anyway, let's look at one of these quark interactions. Minus CD IJ Q bar prime Li H P prime RJ. So that's the whole business there. And then when we rewrite this, we can rewrite it as minus root 2 over V. So here we're going to the vacuum, mean value in the vacuum. This is root 2 over V, then Q bar left. Now these are the mass fields. The mass is sigma D and D right. And I'm sorry, D right and then an H. And so consequently, that thing is minus root 2 over v. So notice, I'm canceling the v. I'm canceling the v over root 2 in h with this prefactor. And so this is the mass eigenstates 0, and then what we have here is v plus h over root 2, sigma d, d right. And so altogether this is minus d bar right, 1 plus h over v, sigma d, d right. Wait a second. No, this is left. I have to follow my notes. So this is the Dirac mass term. The masses are sitting here. The 1 gives you the masses. All right, so that's the mass term. But then there's this term, the interaction. So the interactions are proportional to the mass. So in other words, we have the term minus d bar left, let us say, generation I, mass of the down quark of generation I, times over v times h times down quark right generation I. So everything's diagonal here. So in other words, there's a term that's minus mdi over v, and then there's a Yukawa interaction, d bar li h dri. So this is your standard fermion spin 0 boson, fermion dagger, and a coupling constant. The coupling constant then is the mass over the bed of the Higgs field.
Where did the little h come from?
Little h is in the vacuum. The mean value in the vacuum is 0 v over root 2. Okay? All right, let me toss you a candy. All right, it's a similar term to the up quarks. It's minus 1 plus h over v m up family I u bar left I u right I. Okay, so that's that. Now, for the lepton masses, we first of all have the charged leptons. And so here we have nu E, nu E, nu mu, nu, and all this is flavor. And for a while, in fact, until maybe 20 years ago, people were, or 30, I don't know, 25 years ago maybe, people thought that the flavor and the mass eigenstates were the same because the neutrinos were all massless, and we just had to worry about the charged leptons. In any event, for the charged leptons, what we have is something like this. Sum ij equals 1 to 3 minus c sub e so this means the charged ones, ij, e bar prime, prime meaning flavor, left, I, Higgs doublet, e prime right j. So these guys are singlets under SU2 left. This is a doublet, this is a doublet, so the thing's invariant, and those are the, so plus permission conjugate. And what this leads to is it gives us mass terms like V over root 2, sum ij equals 1 to 3, minus CEIJ, E bar prime, left I, E prime right J plus permission conjugate. And that means we have a mass matrix for the charged leptons, which, maybe I should just, well, anyway. Mass matrix for the charged leptons that's V over square root of 2, and the ij element is C sub E ij. I'll call it M sub E. But it's really for the 3 charged leptons. And of course, what we get is that this thing is equal to LE, sigma E, RE dagger, and sigma E is mass of the tau, mass of the mu, mass of the electron, and that's about 1.7 Jev, I think. Correct me, okay, if I'm off. About 105 or 106 MeV and half an MeV, 0.51 MeV. And again, it's 3 by 3 matrices. Okay. So let's see. Now let's talk a little bit about the neutrinos. If we have a massless neutrino field that's left-handed, then it satisfies this two-component equation. So that's for a massless field, left-handed. If it were right-handed, it would be a plus here. And in momentum space, this is E plus P dot sigma U prime L is 0. And so what we say is that P over E dot J, actually on U prime left, but P say, is equal to minus a half U prime left of P. So I guess I call this P, but it's in momentum space. And P over E, since it's massless, is just P hat. So P hat dot J U prime E of P is minus a half. The minus a half, this is the, well, J is sigma over 2. And so this thing looks like this. 2J. And so dividing through, it's P hat dot J is minus a half. All right, so that's what you have. The neutrino moves along, and the spin is backwards. Okay, now, what we know now is that the neutrinos are massive. We learned this from neutrino oscillations. We still don't have a neutrino scale. And so what we have are mass differences, and it's even worse than that. It's the differences of the squared masses. And anyway, what one way is we could say, well, these neutrinos, they're really Dirac particles. They may be Dirac particles. If they're Dirac particles, then all we have to do is treat the upper ones here the same way we treated the up quarks, and we're done. And in that case, we would have minus C nu ij, sum over ij 1 to 3, E bar left prime I, sigma 2 H star, nu prime right j plus summation conjugate, and this would turn into a sum IV over root 2 C nu ij, 2 bar flavor Li u prime right j plus HC, and so we have some mass matrix M nu, which would be IV over root 2 times C nu ij, and we could write that as L nu sigma nu or nu data. On the other hand, maybe they're not Dirac particles. Remember, a Dirac particle means that you've got two fields of the same mass. You take a complex linear combination, and then you have a particle and an antiparticle of the same mass, and one just doesn't know. The neutrino CKM matrix, by the way, then is L nu dagger L E. Okay, and that's in other words, that's the analog of LD dagger, no, LU dagger. All right. Okay, now let's think a little bit. Always a dangerous thing to do. We've been talking all along here about left-handed fields and right-handed fields, and that means how the fields transform under Lorentz transformations. And that's a distinction that makes perfect sense whether the fields are massive or massless. You can still say they transform this way or that way under Lorentz transformation. On the other hand, if we're talking about particles, the only kind of particles, the only time you can say that a particle is left-handed or right-handed is if it's actually massless. And curiously, the only two massless particles we have are those the photons and the gravitons, as far as we know. Moreover, the possibility, we've been talking here about gauge transformations of SU2 left, and for that matter, UCB. These gauge transformations only make sense if they're rotating fields of the same mass into each other. And of course, the electron and the neutrino have different mass, the up quarks and the down quarks have different masses. So this gauge symmetry only makes sense before the Higgs mechanism breaks the symmetry. And so we're talking then about effectively high energy effects where the Higgs breaking of 246 GeV, that's nothing, that's a rounding error. Like, unit 1. Anyway, so we're talking then about before symmetry breaking. We're looking at the theory of high energies or high temperatures. And in that case, I wrote some new notes, but I didn't print them out to save the department money these times. Anyway, let's see what is the what are the annihilation operators, let us say, for the neutrino? Let's say the left-handed neutrino. Well, it's 1 over root 2 A1 left, I guess I should say, P. And we're here at, we know it has negative helicity because that's what the left means, so we don't need a left there. And this is neutrino. Electron neutrinos. Let's talk about, well, when they're massless, we can talk about the flavor eigenstates because after all, they're also mass eigenstates when the masses are all 0. So it looks like this. That's for the neutrino, and for the electron, and this is something, some annihilation operator, momentum, spin in the opposite direction, type electron plus I, A2P minus electron. All right, so these are the two fields that exist at high energies, and they rotate into each other by means of gauge transformations. Before symmetry breaking, exact SU2 left symmetry, and we know the electron is a Dirac field, so it's A1 plus IA2, so it follows the neutrino must be A1 plus IA2. So there must be, at high energies, two kinds of particles for the electron. There must be 6 different kinds of neutrino particles at high energy. Now, after symmetry breaking, there must again be 6 particles, and well, there could be more though, because here I'm just talking about left. There may be right-handed. Let's go again to very high energy before symmetry breaking. There may be particles of positive helicity that are neutrinos. Again, massless before symmetry breaking and so forth. We just don't know. Gauge symmetry doesn't tell us. If there are, then we have altogether 12 12 neutrino particles. But of course here, once they become massive, this business of backwards or forwards no longer makes a great deal of difference. They just spin up or spin down. So we no longer have 12, we're back down to 6. So there could be 6 massive neutrinos, or there could be 6 massive neutrinos with in general different masses. 3 of them we would call left, and 3 of them we would call right, but because their masses are not really right or left-handed particles. On the other hand, the neutrinos are so light that when they're moving at substantial energy, then they're essentially left-handed. And there may be some others that are essentially right-handed. We just don't know. And so that's one of the huge puzzles of modern physics, and it's really important to get that straight. And so there are experiments being done in all sorts of places. And the leader in these experiments pretty soon is going to be China, because they're building the best underground physics laboratory. So they'll be the leader certainly in dark matter. They probably will be the leader in neutrinos, because if you have a good underground lab, you can do better neutrino experiments. So in fact, China will be the leader in this field. The EU is the leader in high energy physics with the LHC. It's hard to say what we're the leader in except for manned spaceflight, which of course scientifically is totally meaningless. It's like the Roman circuses, which at least were cost effective, whereas manned spaceflight is...
Well, hell, we've given up on manned spaceflight.
Yeah.
We gotta go get a ride.
Yeah, but we're still spending something like 10 billion a year on manned space flight and maybe 1 billion a year on sending scientific instruments into space.
Yeah.
So it's, and the best satellite is the Planck satellite, which is a European satellite. So we're not in first place in any field I can think of, except, I guess, maybe medical research, but so I'm basically sticking out my tongue at Congress. All right, so now we've been talking about massive neutrinos, and I wrote down what the Dirac mass terms are, but there's another mass term, this is called a Majorana mass term. And so let me try to say something about what it is. You can only have a Majorana mass term if for fields that are neutral. And so let's suppose we have 6 different flavors of Majorana field. Then we have something like this. It would be I Mij nu prime transpose right meaning that how it transforms under Lorentz transformations, not what the particles are. Right type I sigma 2 nu prime Rj plus Hc. I'm just getting too tired to write that down explicitly. Now, let me explain why it is that these guys are Lorentz invariant. It actually is very simple, although the notation is not great. Let's just consider one species, and I'm writing double prime now because prime is flavor, and the other prime is image under a Lorentz transformation. Okay, so sorry about that. Right sigma 2 nu right prime. So these are both right, okay? And one could have written this in terms of left-handed fields. We look very much the same. So here is, now what is this under Lorentz transformation? Well, under Lorentz transformation, the right-handed field, nu right prime, is e to the z star dot sigma nu right, or nu right double prime is that on prime. And so what we get here is nu right prime, the adjoint of this, and the Pauli matrices are Hermitian adjoint, so this is e to the z dot sigma. And then we have here a sigma 2, and then e to the z star dot sigma, and then nu prime right. Prime here meaning just flavor. All right, so this is how right-handed fields transform into Lorentz transformations. And now, if we pull the sigma 2 through, what happens? It flips the sign of sigma 1 and sigma 3, leaves the sign of sigma 2 invariant. But sigma 2 wait a second. I think I'm screwing this up. Yeah, I'm screwing this up somehow. Oh, I forgot the transpose. That may be why you were frowning. We must speak up. All right, so there's a big popo in this. All right. So this is really a transpose here. So that means we have z dots. All right, so this is the way the thing goes. The one on the right's right. But now what we have is z star dot sigma transpose. Right? Right, all I did was transpose. All right, now everything is perfect because sigma 2 transpose is minus sigma 2. And if we pull the sigma 2 through, it flips the sign of sigma 1 and sigma 3. So everybody changes sign. This is the same thing as nu right prime transpose sigma 2 e to the minus z star dot sigma e to the z star dot sigma nu prime right, which is to say nu prime right transpose sigma 2 nu prime right. Okay, so that's why the Majorana mass term is invariant. And of course, for the if you were doing it with left-handed fields, you would have a similar thing. Instead of saying it's z star, it would be e to the minus z dot sigma, or maybe plus z dot sigma. Anyway, it would be the same business. You have e to the z dot sigma, say, sigma 2, nu left prime transpose, e to the z dot sigma transpose. Now you pull this thing through, and 1 and 3 flip sign. 2 is already flipped because of the sigma 2 transpose, and so it cancels. So these are the Majorana mass terms, and I don't know, we don't know what the masses are really. The way we know that there are masses is the seesaw mechanism, and the idea is that the phase, as you go along, the change in the phase is T times the change in the energy, and that's LE over P times the change in the T is E over P is the velocity times the E over P is 1 over the velocity, and the distance divided by the velocity is the time. And so this is LE over P, and it's then square root of P squared plus M1 squared minus square root of P squared plus M2 squared. And now you expand them, and so what you get here is approximately L delta M squared over E. And this is in natural units. In unnatural units, it's that times C cubed over H bar, apparently. These things have been measured, and so we've learned about delta M squared, and basically what we know is that delta M squared 1, 2, which is to say M2 squared minus M1 squared, is something of the order of 7.5 10 to the minus 5 eV squared, and M2 squared minus M3 squared is something like 2.4 10 to the minus 3 eV squared. And these numbers are a couple of years old. I tried to find the newest numbers from the PDG today and couldn't find them. But of course I didn't look for hours. I mean, I looked for minutes. Couldn't find them. All right, any questions? Let's quit. Oh.